The last portion of this lecture, we're going to talk about Earth's interior. We're going to talk about how we've used scientific observations to learn about Earth's interior, even though we can't drill down into it directly and learn all about it. But we can learn about things indirectly and test different hypotheses. Let's begin. I'll have you start by thinking about what you've learned in the past about the interior structure of Earth. See what you can remember from any past courses where you might think, okay, Earth is this sphere, and if I cut into it like a cake, we could look at what the interior of Earth looked like. Try for yourself to sketch and label just a diagram of what you know or what you think about the interior of Earth right now. Pause this video and come back, and then we'll go over a little bit more about it. You probably saw at some point in your coursework that Earth was made of some sort of set of layers, kind of look like an egg or a peach or something like that. Something like this, perhaps. And then at some point you probably thought that, oh, well, in here is all the hot lava, and there's something going on in the core, and I saw some movie about the core at some point where they blew it up and saved Earth or something like that. I don't really know. The point is that you know probably that Earth is made of layers. And we're going to talk about what these layers are and how we know what those layers are and what they're likely made of. So we've mentioned that Earth is a system. We've talked about these sort of exterior subsystems, the atmosphere, cryosphere, lithosphere, hydrosphere, and biosphere, and what drives those. But we can also talk about just the Earth's interior extending up into the lithosphere as the plate tectonic system. So interactions among the lithosphere, asthenosphere, which is part of the Earth's interior, and the deep mantle. And we can talk about the interactions between these subsystems and the way that they are going to work on one another. And in particular, how the plate tectonic system is partially driven and informed by the Geodynamo System, which is made of the outer core and the inner core. So let's look at one way to classify the layers that make up Earth. One way, and this is one of two, this is by composition. And it's got four broad pieces. It's got the crust, it's got the mantle, it's got a liquid iron outer core, and then it's got the solid iron inner core. Crust, mantle, core. The crust, now because we're classifying this in terms of composition, we're going to talk about the stuff that makes it up. So the crust, that stuff is silicate minerals. We'll learn a little bit more about what that means, but for now, just realize that it means minerals that are largely made of silicon and oxygen. We've got a lot of those on Earth, and so we've got a lot of them in the crust. Silica, SiO2, is a piece of all of those minerals. And if it's just SiO2 in the mineral, it's going to be called quartz, which makes up lots of sand on Earth's surface and parts of many different rocks. But there's also some other minerals that contain other metal ions. And we'll learn a lot about those minerals in the first part of this course. The feldspars and the micas and olivine and hornblende and all these other minerals that also contain a lot of silicon and oxygen, but also other metal ions, because those ions are somewhat common on Earth's surface too. So that's the crust. It's the very outer skin of Earth is what's made of those silicates. Similarly, the mantle, this part in here, this big layer, is also made of silicates, but they're a little different. There tend to be more metal ions, lots of iron and magnesium in that mantle, and some other stuff. Crust and mantle, they have similar but not equal compositions because they're both made of silicates. And there are important differences that we'll talk about in terms of their composition, and even compositional differences within the crust. The core, in contrast, is mostly made of metal. It's not silicon and oxygen, but it's mostly metals like iron and nickel and some accessory stuff, 1 or 2% of some other things that scientists are still not entirely sure what it is, but there are ideas that carbon could be important, or sulfur, or maybe some other metals that are important in that core. So in contrast with describing Earth's interior in terms of composition, we can also describe it in terms of physical properties, really the material strength of what makes it up. And so in this model, we still have part that's the mantle and the outer and the inner core, but we're not defining them in terms of the fact that the mantle is silicates and the core is metal. Here we're saying first we'll start with the core itself. The outer core is liquid. Its physical property is that its phase is a liquid, and the solid inner core. So that's a little more important when we're talking about this way of classifying Earth's interior. And then if we look at the upper layers above this part of the mantle, we've got a few different layers. We've got the lithosphere, the asthenosphere, and then we've got the upper mantle, and then finally the lower mantle underneath that. So the mantle is still there, but the name crust has disappeared. The crust, if we think about that compositional part, is just part of this lithosphere. So the lithosphere here is the solid and rigid, that's important, meaning relatively inflexible, exterior of the Earth. And it consists of Earth's crust plus a bit of upper mantle, the uppermost mantle. So we don't talk about the lithosphere as being made of silicates, although it is, because the lithosphere is really, that's describing its physical properties. It's solid and it's rigid. Now, most people think that we have this ocean of magma or lava under our feet that's liquid rock, but we really don't. This asthenosphere here is still solid for the most part. But unlike the rigid lithosphere, it is ductile or flexible in some way. It moves a lot more like silly putty. If you've ever seen silly putty, right? It can bend and move and it deforms and doesn't totally keep its shape, but it's still a solid. You won't spill it on the floor. It'll fall out as one big piece. When you get to this depth inside Earth, the solid rocks there are so hot that they behave more like silly putty than they do like the rocks that you're used to. And they can flow at a very slow rate. It's not liquid, but it does flow very slowly. So that's the difference between describing things in terms of composition, that's crust and mantle, or in terms of physical properties, where the exterior of the Earth is the lithosphere and the asthenosphere. So there's a zoom in of that, just so you can see that a little bit more. Lithosphere, remember, is the crust, both continental and oceanic. Turns out those are different. And the upper mantle. There you go. In addition, I had mentioned that there were differences in pieces of the crust, that certain types of crust are different than other types of crust. So when we talk about the crust, remember we're talking about silicate rocks mostly, but the continental crust is made of lighter rocks, less dense rocks. And they literally float on material of higher density. They float on top of the upper mantle. So the continental crust here is 2.8 grams per cubic centimeter. That's a measure of density. It's mass divided by volume, and that's a density. Whereas the mantle is 3.4 grams per cubic centimeter. In contrast, just so you have an idea of how much this is, water is 1 gram per cubic centimeter. So rocks are about 3 times, give or take, as dense as water, right? If you had a particular volume of water and you had the same volume of rock, the volume of rock would be somewhere between 2.8 and 3.4 times as heavy, probably. The continental crust has a density of 2.8 grams. The oceanic crust, the crust that lies under the oceans, it turns out, is more dense, 3.0 grams. But both of them are less dense than the mantle. And as a result, they're going to float on top of the mantle. That's one of those effects of gravity that I hinted at before, because gravity is pulling on both of these, but the force exerted on the denser stuff is greater than the force exerted on the less dense stuff. So the less dense stuff ends up rising on top. Now, it's not going to rise so high as to rise above the water, which is even less dense, right? That water is going to sit on top of the more dense crust. And then the atmosphere, which is even less dense, like 0.01 grams or less per cubic centimeter. I don't know off the top of my head what its density is, but it's way less than water even. The atmosphere is going to sit above that. You're not going to have floating continents, sadly, because of gravity. At least floating continents in the sky or on the ocean. Instead, they float on the mantle. To give you a sense of how thick Earth's crust is and the features on Earth's surface, right? We have the typical elevation of the land surface, so that's the continental crust is 0 to 1 kilometers. And Mount Everest here is on the order of 10 kilometers high. It's about 30,000 feet, which, yeah, give or take, it's about 10 kilometers, right? Plus 10, there it is. If you look at the ocean floor, though, most of it is not just a little shallow. Most of it is way deeper than that, right? Typical ocean depth is actually 4 to 5 kilometers deep. That's because that oceanic crust is sitting so much lower than the continental crust is, for a couple of different reasons. First, I'll mention the plate tectonic system, though, because the Earth's lithosphere, that solid outer skin, is going to behave in the way that it does due to the plate tectonic system. We'll talk more about that in the future, but I just want to mention this now since we're talking about Earth's interior. And the plate tectonic system describes how the heat energy inside Earth moves around and thus affects those crustal plates. Really, I should say lithospheric plates, because we've got crust here, we've got upper mantle here, and they behave as one rigid lithospheric unit in response to Earth's interior heat in a process called convection. You've seen convection before. In addition to the pictures that you see here, it's what drives thunderstorms and it makes air rise so high and why there's circulation inside thunderclouds. But it also is what drives a pot of boiling water to circulate. See, what goes on is you've got the water right near the burner that's being heated. And most materials, when they heat up due to that extra thermal energy, they expand. And now that they've expanded, they're less dense than the stuff around them. As a result, and in response to gravity affecting the more dense stuff more and them a little less, that less dense material, that hot, less dense material is going to rise. And cooler, more dense material will replace it. In turn, it will heat up. Now that you've got some less dense material that has risen, it's going to slowly cool down and then get more dense, and it's going to sink again. You end up generating these convection cells where less dense material rises, and it's less dense because it's hotter, and then more dense material sinks, and this circulates in your pot of rapidly boiling water, if you watch closely. The same thing is happening inside Earth's interior, and it happens because that asthenosphere and the rest of the mantle can behave in a more ductile way. It's a solid, but it can flow, more like silly putty can flow at a very slow rate. So this is much slower than your pot of boiling water is going to move. But the heat inside Earth's core is several thousand degrees. It's heating, and in response to other things that we'll talk about, it's heating up this mantle material, which is able to rise and generate the same sorts of convection cells that occur in your pot of boiling water. As it does so, it, in some places, pushes some crust up, in other places pulls it, drags it, and pulls it downward. And so these rigid lithospheric plates actually are able to move across Earth's surface at a very slow rate due to this convection. We'll talk more about that in a future lecture. Now, the other subsystem that we had talked about in Earth's interior is the Geodynamo System, in which Rapid motion of the liquid outer core, so that's this metal that's moving around relatively rapidly. It's not, moving at miles a second or anything. It's moving very slowly. But because it's a metal and it's moving somewhat, it stirs electrical flow in the solid inner core, and it causes Earth's magnetic field. This goes beyond exactly what we're going to learn in this class, but if you take a physics class where you learn electromagnetism, you learn that moving charges is what causes magnetism. So it stands to reason that a metal flowing around is going to cause a magnetic field. That's important for a few different reasons that we'll talk about as we go on in the course. But know that Earth's magnetic field is a result of the core. So we've got some motion inside Earth that's not due to the sun, that internal engine that connects plate tectonics with convection cells and with the geodynamo ultimately inside Earth's core. But there's another source of energy on Earth. And we said that energy is what's required for all changes in matter. So it's important to learn about that too. The sun is what drives Earth's external engine. Solar radiation is responsible for most of our climate and weather because that energy coming in causes changes at Earth's surface. Again, we'll talk more about this in a far future lecture. Whereas Earth's internal engine is powered by trapped heat and radioactivity, sort of ongoing generated energy that is a result of quantum mechanics and things that we're really not going to want to talk about too much in depth, but we'll get into a little bit more. Now, I mentioned that our study of Earth's interior is a scientific one. So we should be able to talk about how we know what we know about Earth's interior. So we can't drill down. We have never penetrated Earth's lithosphere even. We've never even seen into the mantle. And I don't think we've ever drilled all the way through the crust. We've really only drilled a few kilometers through Earth's surface at any point. So how do we know what we know? Well, we have measurements of Earth's total mass. We can see how it moves through the solar system. And our understanding of gravity and the way that the other planets move, we've come to understand that Earth's total density is about 5.5 grams per cubic centimeter. But like you saw, we measured those surface rocks, and Earth's continental crust was about 2.8, and oceanic crust was about 3.0. At max, 3.5 grams per cubic centimeter. What does that mean? That means that there's got to be more dense stuff somewhere. Okay, so that's one hint. Somewhere inside. Now, we can also measure seismic waves. We've set up these seismic detection stations across Earth. Today, they help us detect where earthquakes occur and how far away those earthquakes are. They were actually set up originally so that we could figure out when other countries were setting off atomic bombs. But today, we mostly use them to study earthquakes. We've learned that these seismic waves, these waves that move through Earth, PNS waves that we'll learn a lot more about later, they move faster where it's dense and more rigid, and that a certain type of S wave, waves that look like a sine wave that go up and down, they can't pass through liquid because the liquid doesn't have shear strength. So that means if we see S waves pass through stuff and we can detect them, those waves on the other side, that means that it must have passed through solid stuff. And we can learn this to realize that Earth's mantle is solid. Otherwise, we wouldn't see S waves on the other side. But this is also how we learn that the outer core is liquid, because those waves don't pass all the way through Earth. They get blocked by that core, at least the outer part of it. So like I said, samples, we've only drilled, there you go, there's the number, 12 kilometers down is the deepest we've drilled in this Kola super deep borehole. Really deep drilling spot, right? You drill this mine all the way down and then this borehole goes another 10, 11 kilometers. But we actually have rock samples that have been brought up from depth by plate tectonic processes and ultimately by volcanoes from about 500 kilometers depth, we estimate, based on the composition of those rocks. And we see minerals that are much denser than surface minerals, but they're still silicates. for the most part. That tells us, okay, Earth's pressure is definitely higher inside, and it's probably still made of silicates, at least down to 500 kilometers down. We can do some experiments at Earth's surface where we take these things called diamond anvil cells. So you see a diamond here and a diamond here, and you press them together really, really hard. That's all a diamond anvil cell is. And we can use that to study what happens to rocks and minerals and different materials at very high pressure. And if you heat them, you'll also get the high temperature conditions that we find inside Earth. We can use modeling to tell us how hot and pressurized it must be at different levels of Earth, given the stuff that's overlying it and given the rate at which heat is being emitted by radioactivity in Earth's surface and things like that. Modeling is a way for us to describe phenomena quantitatively and make predictions by adding together all of our physical laws. So, right, we know what goes up must come down. We have a law that we can use to describe the effect of gravity. We have different laws that are related to things like thermal diffusion and radioactive decay that we can use to, with it some error, but not a ton of error, predict how hot and pressurized it must be under a certain mass of material on Earth. So modeling is important too. Now, one really cool piece of information that we get is from meteorites. We think that meteorites are stuff that was left over during formation of the planets. Leftover stuff during solar system formation. And if we look at those, we see that some of them are made partially of this iron nickel metal. So there was probably a lot of iron and nickel floating around in our early solar system. Stands to reason that really dense spot inside Earth, given the fact that it's magnetic and it's really dense, iron nickel metal is a pretty good guess for what that stuff is. And I'm way oversimplifying the sorts of things that we've done to test this hypothesis, but just to give you an idea. We also see some that are these metal mixtures with silicate minerals. So we've got metal here, and then we've got silicate minerals here, right? So that stuff had some silicon and oxygen and other cations in it, but it's different than the iron nickel metal. And what we think is that these formed during formation of some other protoplanet, right? As you had asteroids basically collide together, they're going to heat up this stuff, and you're going to start to differentiate or separate out different materials because they've started to melt. And so the thought is that dense iron sank and that lighter silicates started to rise, and that these sorts of meteorites that we found that have both of them in them are from this very early stage of separation. So some planetesimal somewhere was starting to differentiate into different pieces that were just starting to rise and fall, like you see in this diagram over here. And then it got blasted apart because it got hit with an asteroid that was too big. Using these meteorites, we can learn something about what the likely interior of Earth and other planets in the solar system are made of. So that covers our very short introduction to geology. We've seen sub-lectures on why we study it, what it means to be physical geology. We've learned about systems and how Earth is a system. We've done a very brief overview of geologic time and how geology functions as a science. And then we've looked at Earth's interior and some of the information that we've used to learn about Earth's interior. If you don't remember going over any of those, make sure you go back and make sure that you've seen each of the videos for this lecture, because the start of the course is not a great time to fall behind. So go ahead and watch any of these again that you don't remember at all. And please, if you have any questions about anything you've seen, get in contact with me, your instructor, either on Zoom or on the discussion board. Thanks for watching and listening. See you next time.